Next presenter we're going to bring up is Chen Fang. He's the owner of Zetar. He's excited to tell us about moving massive amounts of data across distance, which dovetails nicely into these type of discussions about multi-data centers and cloud adoption.
I guess I can say good afternoon, everyone now. And then my name is Chin, and I like to share with you some of our experience distilled from 6 years fighting with a very, very demanding situation, okay, and the problem. So since I only have 20 minutes, so let me go fast. So first of all, for the audience, most of the audience in this industry know moving data is very critical task. But for some of you who maybe PhD students who are not familiar with the background, I will provide you a context. So this is Mr. Navin Shenoy, okay? He is the EVP of Intel's biggest group, data center group. And he said in 2018 August that 90% of the world's data was generated in the past 2 years. So counting from August 2018, that's 2016. And look at the next one, which is really stunning, even to seasoned IT professionals. Only about 1% of the data is utilized, processed, and acted upon. Why? It's because the poor data mobility solutions available. So now, by the way, my talk covers pretty much the scope described in the abstract of my program statement, okay? So if you want to know the state of the art, and then an easy way is to look at the participant and their solution types from, say, Supercomputing Asia 2020 or Supercomputing Asia 2019. Why is that? Because this Supercomputing Asia Data Mover Challenge is probably the highest level data mover, software data mover solution competition in the world in the past decade. So you normally, it's by invitation only too, okay? So if you look at their solutions, they are probably what you call state-of-the-art. Now, I like to also talk about some common misconceptions. One thing, especially even including the energy industry, is using firewall. I will tell you a story. So one time I had a question from an East Coast medical institution, which collaborated with the West Coast in San Francisco. And they had a 10G connections between the two institutions already. But they were wondering why they got such a low throughput. It turned out the firewall on the San Francisco side is only 1 Gbps, so you cannot say 1 equals to 10. That's it. The other common misconception is use virtualization. If you go to, say, Amazon, and go to Azure, and go to IBM Cloud, you may find even these cloud providers provide physical instances, not just virtual machines and containers. Why? Because for IO-intensive workloads or tasks, okay, virtual machines may not be a good fit. So you might want to use containers or even go one step further and use physical instances. The third misconception is the proprietary protocol is better than TCP. That's plenty untrue, patently untrue, I may even say, okay? The modern TCP is very well designed, very well tuned. So if you use it properly, then it's good for many, many things. And the fourth one is something that people keep talking about, AI, machine learning, deep learning, and all that. But they missed, many practitioners and the device makers missed one important thing. They always use lots of small files. That's what the loss stands for, okay? But small files typically introduce such a heavy overhead. It's just a simple law of physics. If you want to aggregate a certain amount of data, if you have numerous small files, the file system just have to do many, many, many more IOs in order to accumulate that amount of data. That just doesn't give you high throughput that AI, such as GPU cluster needs. The fifth one is create data lakes. I mean, it's a very biased view. If you say a supercomputing center, a national one, certainly you want to have a large storage capacity. But if you are just a university lab, why you want to create data lake? It's costly to operate. It's also data lakes requires plenty computing power. Do you have the budget for it? So let's just keep going. So this is a very important one I'd like to share with you, okay? A lot of people don't know that data movement solutions has 3 essential categories. The first one is what we call data access solution. Typically, it's end-user oriented. And so the data stays where it is, and the user access data amount is small, so it's okay. But it's getting less and less important because the second one, the data transport solution covers what we consider most important today. That is, majority of the data is machine generated today. For instance, we deal with, say, linear accelerators, which has tens of thousands of detectors along the 3 kilometer long accelerator. And their rate of spitting out data would probably take a few million people keep clicking on their iPhones to catch up, okay? No way. Human beings are no longer the major data generator anymore. So this transport solution is important. I also mentioned this keyword, the co-design mandatory. What is co-design, by the way? DOE, Department of Energy, around early 2000 had already foresaw the need of making the I/O and the computing more progressive. So he introduced this co-design concept. Basically, it means considering storage, computing, networking, and software design in an integrated manner. I can only say high level, given the limit of time. So if you do this, then most likely the design will be better. Now, this is for a situation where the source, that data at the source must be moved. For instance, in the energy industry, when you do a seismic study, the data has to be moved either to your data center or to the cloud. There's no escape. Now, the third one is where most misconception nowadays happens. It's data aggregation is if you have like a data traffic generated using different transport solutions independently, and you route them through a certain connection, maybe say 8 times 100 gigabits per second or something, and then you can achieve outstanding bandwidth utilization. But that's data traffic routing. That's not data transport. Okay, so that's actually is called a software-defined WAN operation. And I mentioned 3 examples. They are pretty established. Comcast did it in 2013, 1 terabits per second over 100 gigabits per second link. Google has done that for its B3 project. ES9 did it with a 2 times 200 between Oakland and Berkeley for migrating the NERSC from Oakland to Berkeley. Okay, so they are different. So this is the most dominant and it's most challenging. Now, I like to share this with you. I've been using it at various SE events, starting from SE Supercomputing 16, and it's pretty well received. I'll try to make it as clear as possible. So this is for people coming from California. You know, the Bay Area water transport is provided by the Hachi Hachi project. From the Hachi Hachi Reservoir in the Yosemite area. What are the 4 major elements of this water transport project? If you think for a minute, do you know the answer? I'll give you the answer now. The first one, most essential one, is a reservoir with water. When California was suffering dry seasons, no matter you have the rest of 3, pumps, electricity, large pipes, doesn't matter, poor water flows. For water transport, same thing. If you do not have enough storage capacity, throughput, don't even bother. Even you have a cluster of a scale of data mover software, doesn't matter. And you have to, the data mover software has to be powered by computing power. And then finally, you have to have like a fast enough pipes in order to achieve high scale throughput. And the important key point is here, you have to get the infrastructure ready first. This is not software alone, neither is a network alone endeavor, okay? Now, So I mentioned that in the abstract we did 2 projects. This project was almost semi-still for half a year. It's a project we did it together with AMD, Benelux, and Samsung. And the objective is see if the Samsung's prototype KV SSDs could be an efficient replacement of block-based SSDs, okay? And we wanted to show the results before SC19. And so it was very compressed time frame for us to do. So you see those boxes. Actually, you are seeing two clusters. Each cluster has 2 yellow boxes, that's a storage node, 2 orange boxes, that's a data transfer nodes, okay? And we were given only about 2 weeks to do the integration. Back then, all the hardware, everything, including the EPIC CPU, the most high-end type, okay, from AMD, they were brand new. And the CPU is not something trivial. You have to know the architecture in order to utilize it, such as a numer property and etc. Okay, but we were able to very quickly reach the 90 plus Gbps for certain data sets. So the next project is a multi-state project, which we also were aiming to show it before SC19. This is a kind of a historic first project. It's from ICM in Poland, Warsaw, Poland, to Singapore. And this is the undersea cable system that was used. And it's very interesting to know about this, because this is the world's newest 100G connection, okay? And it's routed through the Red Sea and the Indian Ocean. So by having this, the countries along this route, okay, now they have a 100G on-ramp to the world, okay? Before, I will show you later on, I must save time now. So finally, I will show you what we plan to do. Before the end of this quarter, we will introduce the parallel streaming, which some of the speakers here already mentioned, and that they intend to use it. Parallel streaming is different from the consumer streaming, because when you have multiple sources and multiple destinations, streaming can be extremely difficult unless you utilize your data type wisely. So now, hold on. How come it doesn't go down now? Okay, now the main part. This is where I want to spend most of the time. You wonder, hey, Chin, why you did that long distance transfer? Yeah, sure, the distance is 12,000 miles, but what's the big deal? Actually, there is a lot big deal. If you see this, alpha, concept alpha. This is a project and the concept introduced and formulated by my former Slack co-PI, Dr. Les Cottrell. He is credited down here, okay? You will see among the world's high-speed connections, 10G, 100G, they have a different alphas. For instance, crossing the Pacific, the alpha is typically around 0.3. But once you get into like a Middle East and the Mediterranean area, the alpha is pretty low. So that tells you that the so-called round-trip time for a connection is just one aspect. You have to, the alpha actually incorporates other concepts like the physical properties of the connection. So the connection we did in the previous example, that's the newest 100G connection. Nobody has really used it for production work, okay? We were the first one. And I can tell you this from our experience. It was difficult to tune for the transfer setup to utilize it more optimally. Even though the round-trip time is only 173 milliseconds, it was more difficult than the route we did before, 233 milliseconds. So now, why this CAE one? Because before, this is before in early 2019, from Europe and Asia, there's only one 10G link. Now, once in August, after August, there's this 100G CAE one, collaboration Asia and Europe one, okay? This 100G link. What was the 233 millisecond one? That's from Singapore to Los Angeles, and from Los Angeles to Chicago. That's the long route we did. And it's easier than this. That's only 173. So for any new connection, your service provider provision for you, you have to test it. Now, what was the server used on both ends? On the Portland, Washoe side, it's just a single, almost like a desktop type machine. On the Singapore side, it's a 2U machine. And both are made by Supermicro. The models are there. Now, here is where it gets interesting. So how the CAE one is operated by 6 providers, both European and Asia, okay? So they have a very strict fair use policy. So we only granted up to 80 Gbps out of 100 Gbps. How can we qualify that they really allocated that much bandwidth to us? So we used a very simple tool. Everybody probably, and most people in the data management probably know, it's called IPER3, which is created by a US DOE's ESNet software group. And we fired up 6 instances on the ICM machine, 6 client instances on the Singapore machine, and achieved over 12,000 miles this using the IPER3's TCP mode. You know, IPER3 is a really primitive tool, but this tells you 2 things. One, the concurrency of your software is really important. Secondly, proprietary protocol doesn't really do you much good because IPER3 is a really primitive tool, okay? Look at this wavy shape. Now, if you see a professionally designed using modern threading model, see the same memory-to-memory test, 80 Gbps, it's very flat. Concurrency and threading model is very important. If you add like distributed architecture, that's even better. And I do not have time to go into further detail, but you are welcome to talk to me. Now, on the ICM side, there are 2 raster file systems, 2. And all of them are made with traditional hard drives, SATA hard drives, 7200 RPM hard drives, Western Digital ones, okay? So they are connected to the machine with FDR, 56 Gbps. So how can you, unlike Ethernet interfaces, you cannot bound InfiniBand interfaces. How can you do that? That's where the software has to do the job. The software has to be taking care of the aggregation of the 2 file systems throughput. So if you see this is measured, and then typically we try to reach at least the 70% aggregation efficiency. So I will just show you. Oh gosh, what is that? This is like a race against time. Okay, so this is the aggregation done by the transfer software. Here is one key I like to share with you. Using parallel file systems, especially parallel file systems formed using hard drives, takes a lot of trial and error. I will mention one key concept here. Parallel file system, the word parallel means you must utilize that characteristic intelligently. You see many tasks. We do parallel tasks in order to drive up the throughput. And secondly, they are hard drives. So the hard drive characteristics are different from, say, NVMe or SATA drives. How can you specify the storage interaction properly, whether you use the Linux page buffer or not? Okay, that you have to be careful. I can only say this to you. You have to be careful and try it out. Now, let's see. I think yeah, that's it. So any questions? I have 1 minute for any questions. I will be around, so feel free to talk to me. Some of the concepts may be too rushed, I rushed over too fast, but I'm here to answer questions.
Any questions for Chen, the question man? So I think one of the things we've challenged Chen with, or maybe challenged himself with, is how to stream data through water. We've had some of these talks about subsea nodes and data acquisition under the ocean. So these are the kind of challenges he starts to think about when he comes to these events. But
Yeah, and
okay, I have a
also,
question back here.
Yes.
What's an alpha value? Is that the quality of the fiber? Or I just missed what an alpha is.
Alpha basically is defined as the physical distance divided by the actual fiber distance. But that's really just the most basic level. Why I said that? Because the optical devices you used along the path can have like a dramatic impact. Also the physical environment. Remember I showed the slide that shows around the Mediterranean and the Middle East, the alpha level tends to be low. I suspect the environmental factor could be a big factor in that. And that affects the transmission quality. So even RTT cannot tell you the full story. That's what I try to drive the point to you. And if you want to, you can go to Samsung Forum, okay? Look up Dr. Les Cottrell's talk about this particular one, and he will provide more details. He has done this for several decades. Yeah, it's called Internet Monitoring Project. So don't think RTT or so-called round trip time represents the most fundamental property. No, not really. You are talking about physical stuff. So the physical property of the link connection is important too.